hey there. Apparently I'm trapped in the screen. We'll try to make do. So, I hope you had a good night and welcome back. Today I want to talk a little bit about something called the properties of matter. And recall last time we talked, we defined matter. We said, this is anything that's got mass and volume. We said that matter is the stuff that makes up all the stuff in our world. And I want to talk about how to talk about that stuff. I want to talk about how to describe the universe around us, talk about how to describe the chemical world in which we live. And through the magic of film editing, with just a simple clap of my hands, I can make it appear on the screen here. So, the first thing I want to do is talk about physical properties. Physical properties describe a pure substance. Now, a pure substance is a substance that's made of one thing and one thing only. So, a pure substance might be like this piece of aluminum foil. It's an element. It's made of, aluminum, which has been rolled very thin. Maybe I have another element, sulfur. Sulfur is in here, it's in the jar, we'll talk about sulfur in a moment. Maybe I have something pure, but maybe it's not an element, maybe like a stack of papers here. Okay, as long as this is relatively homogeneous. As long as this is made of the same kind of stuff, that there's not paper in here, and in the middle of the paper I find a piece of foil or whatever. I can still talk about the properties of whatever this is made of. Or maybe I got a pure substance that's like a pure compound, like a container of table salt, or a sample of ammonium dichromate, or whatever it be. Okay, a pure substance. And I want to describe its physical properties in a way which I can observe. That means I can use my laboratory. That means I can use my eyes and my instruments to talk about it both qualitatively and quantitatively. And I can do that, and I can do that without changing the chemical makeup. If I want to talk about my sulfur here, and I go into a lab and I burn it, it's not much good because the sulfur is gone. I can't talk about what this is anymore. I want to just keep this what it is and talk about it that way. Actually, let's talk about the sulfur. You see, the sulfur is a good example of the different ways we talk about physical properties. So if I look at this, it's kind of a pale yellowish color. It's powdery. If you smell it, it's got this really strong kind of unpleasant rotten egg smell. It's something you'll smell in lab, or maybe you've smelled before, because this is found near hot springs. It was called brimstone for a while. And it's an important ingredient to gunpowder. It's in medicine and fertilizers and lots of different things. Well, if I'm talking to a chemist and say, I found this weird yellow rock, and it kind of smelled like rotten egg. You guys go, you're talking about sulfur. It's not that weird. It's everywhere. But to be sure, I could talk about it even more. I could say, here, give me a sample. Let me weigh it, and let me find its volume, and let me find the density. If that matches sulfur, and the smell, and the color, I'm pretty sure I know what I'm talking about. But you know what? I can even do more. I can check how hard it is. Now, this sample of sulfur is powdery, but I can measure this, and its absolute hardness. That would tell me a bit more. If I want to be super sure, I can even check for more things. I can look for its boiling and melting point. You say, but Mr. Nett, if I boil and I melt this, then what I've done is I've changed its chemical composition. I went from sulfur to a liquid, or I went from sulfur to a solid, if it was liquid to start with. Of course, I am changing states of matter. But change of matter, that's a physical property, because I am going from sulfur of one physical state to sulfur of another physical state. These things here, all those are is changing it from one kind of matter to another, while not changing the chemical makeup. It's still sulfur. So if I know all these things, I can describe and say, I've got sulfur here. Of course, I could just come over and read the bottle I took it out of too, but, to the point. And so that's what we're talking about with a physical property. Now, there are different kinds of physical properties, and with the magic clap, I can make it appear on the screen. So, the first kind of physical property is what we call intensive. Intensive properties. An intensive property is a physical property. It's the kind of physical property that does not change, it doesn't change, with the amount of substance present. So get back to my sulfur here for a moment. I've got sulfur in two different quantities. I have a full stock reagent jar, and I've got some here on a watch glass. Clearly, the color between the two is the same. The smell is the same. Maybe the amount of smell is, but the smell itself is the same. It's the same odor. Right? The density of what's in here and the density of what's on here don't change. Even though the mass of these two things are different, even though the volume of these two things are different, they're both at the same ratio to each other. They're both the same density. If I try to boil this, sure, it's going to come to a boil much more quickly than this is. But eventually they're both going to come to a boil. And this one will come to the boil at the same temperature. So that means that I have an intensive property. An intensive property. Now, if I have an intensive property, of course I need to have something that's the opposite of intensive property. And the other one appears. And the other one is the extensive property. If we just talk about intensive properties, then the extensive properties are the ones that do change when I have different amounts. The properties that are different between my small and my large sample are the same thing. They're physical properties still. They're just not quite as useful for identifying things. Like a physical property which changes with the amount of the mass, of course. The length, the volume, the amounts, basically. So if you want to think about it, intensive properties are like the properties of the matter as a result of what it's made of. And the extensive properties are the physical properties talking about how much of it I have. So if I have an extensive property, it's still going to change no matter what I have. But the ratios of these extensive properties tend to lead me back to intensive properties. In other words, the amount of mass I have is going to be directly related to the volume as long as the pure substance is present. By mixed substances, things change. Now, these are our physical properties, but what about another one? I have another one. So if we talk about physical properties, then the other side of the same coin are the chemical properties. The chemical properties are things that you talk about with the chemistry when you measure them in such a way as they do change. A chemical property describes the ability or the inability of a chemical to combine with or change into one or more other substance. That's really quite simple. So back here with my sulfur yet again, sulfur has a chemical property. If I ignite it with some activation energy, like from my torch here, in the presence of atmospheric oxygen, it's going to burn. Now, you can't really see it here. You can just see a little bit of smoke rising off of it. That in itself isn't useful to me. You can't see what's happening here much. So that wasn't my brightest idea. I've done this reaction several times before in my life, and I'm well aware it made smoke. I just didn't think the mass I had here would be enough to make enough smoke to be an issue. But I definitely did, and in the interest of not setting off the school's fire alarms on a Sunday evening when I'm the only person here and having to explain on Monday morning why the firemen showed up, I'm going to move this over to the fume hood where we can watch it in complete darkness and take all the smoke outside so I don't have to make an uncomfortable explanation here in a couple of days. So instead, let's hold that thought and move on over to the fume hood. So I went over to my fume hood, and I remembered that I've got the microwave in there from our last experiment. I didn't really feel like moving it. So I just found a video on YouTube of the same experiment because, let's face it, this is a common one. And here's a guy just putting some flame on some sulfur, and you can see him melting it. Those brownish blue balls there are liquid sulfur. He hasn't actually made a chemical change there, right? The brownish black ball there is just sulfur. It's liquid sulfur, which is different than the pale yellow color. It's got this dark color. But on top of it, you might see that gentle blue flame in the shadow. It's hard to see in this case. It'd be much better if you had turned the lights off, but so it goes. That's the chemical change. That's the sulfur turning into something else. That's the sulfur reacting with atmospheric oxygen, in this case, to make something we call sulfur dioxide. And sulfur dioxide, if you're wondering, if it gets in your eyes, stings quite a lot. It makes you cough if you breathe it in. It's not a very nice chemical, but so it goes.
As we talk about chemical properties, we're talking about these things, like the fact that the sulfur burns slowly and makes a blue flame and combines with oxygen to make SO2. The way it interacts with the chemicals around it. That's a chemical property. You can see how it's different than density. It's just like, oh, it has this number of grams per milliliter, or the color, or something like that. These are how it changes and interacts, how it plays with other chemicals. So it's a little different. I'm a little bored of this reaction already. I'll be completely honest. Like, I would have covered it up long ago and moved on. But he is still here because, hey, he's burning some sulfur. And unlike me, he's got the luxury of not watching a cloud of smoke drift towards the smoke alarm with panic in his heart. So, we'll watch it. And, hey, there it goes. He's smothering now. You can see the smoke from it going up. So that's a good example of a chemical property here. So let's go on over to the other room again. Actually, let's talk about this picture for a second. This is a real picture. This isn't someone's drawing. This is a volcano on Earth where there's a large deposit of sulfur, and sometimes when the volcano goes off, the sulfur starts burning, and it has that characteristic blue color. And it's really kind of awesome to look at. And so from the chemical properties that this has to be sulfur in the picture, because that's the only thing that burns with that color of blue and oxygen that way. So I can identify just from the picture, and that's what a chemist cares about. I mean, that's kind of interesting. I want to do one other thing today, which is look at how to do math with conservation of mass. If we know chemical properties, and we know a little bit about how reactions work, then I should be able to talk about those reactions in a more quantitative way. So let's switch over from looking at me or from reactions to kind of looking at a digital whiteboard. Let's pull that up here. All right, so let's start off with an example. In a reaction, 22.3 grams of sodium, which we sometimes write Na, completely reacts with 79.9 grams of bromine, which we normally write Br, to form some mass of sodium bromide, NaBr. And I want to know the mass of the product formed. Well, to do that, you normally need stoichiometry and some math. And you don't know that yet. You don't know about balancing equations and the way these chemicals interact and all the things that would normally be used here. But you do have a trick up your sleeve in this case. And that's the law of conservation of mass. And you happen to know that the mass of the reactants, that is the things that are there before, equals the mass of the products. And as a matter of fact, this is the only thing you know about chemistry at the moment. Well, in this case, it's pretty easy. I've got some sodium. Na. As a matter of fact, I have 22.3 grams of it. And I've got some elemental bromine, Br. And I got like 79.9 grams of that. And I'm going to add these two things together because when I'm done, I get a new chemical called sodium bromide. And I get some amount of it. But in this case, isn't it true that my mass of all my reactants here, mass react, has to be equal to the mass of the bromine, because there's no other chemicals sitting over here, right? I don't have anything else here. I'm only making the sodium bromide. So if I'm only making the sodium bromide, then all of the mass of the sodium and the mass of the bromine, they have to be combined together. Otherwise, I'm not getting anything. So, here I get something really easy. I get something like 79.9 grams plus 22.3 grams. That's going to be equal to like 102.2 grams. And a few of you might be like, oh, but Mr. Nendick, you don't have the right number of significant figures. Like, look, you got 3 here, and 3 here, and 4 here. Well, that's true. Except remember, this is addition. In addition, we only care about the decimals. So since each of my terms have 1 decimal, my answer needs to have 1 decimal. And so this is the correct answer, 102.2 grams. So if I carry out this reaction, which don't, by the way, it's terrifying, I'd end up with 102.2 grams of sodium bromide, ideally. Even if I didn't, because this doesn't make anything else, all the unreacted reactants, all the things that didn't turn into sodium bromide, the elemental sodium and bromine, would still be left in my reaction vessel, and the mass should still be 102.2. Let's take a look at a little bit harder one. Let's look at another one. 12.2 grams of methane react with 24.5 grams of oxygen, and that makes 26.7 grams of carbon dioxide and some amount of water.
And my question is just how much water? And this question would be difficult, again, if I didn't have the law of conservation of mass. Because I do, it's pretty easy. Remember, the mass of my products equals the mass of my reactants. That is, the left and the right-hand sides have to be equal. Well, let's abbreviate methane with a big M and oxygen with a big O. And what's color code those? Those are my reactants. And I've got over here some carbon dioxide, let's just call that C, and some water, W. Now, of course, this isn't how chemists would actually write this. Like we'd say, what, CH4 and O2 and, CO2 and H2O. But you know what, let's just keep it simple. I've got these products and reactants turning into each other. Well, I know that this mass here and this mass here have to be equal, right? There's nothing else going on in this reaction. And I know I have over my methane, I've got 12.2 grams. And I know my oxygen, I have like 24.5 grams. And over here, I know I have 26.7 grams of my CO2. And I don't know how much water. Well, 12.2 plus 24.5, that's just 36.7 grams. And 26.7 plus X. You see how I've kind of set up a little algebra problem here. 26.7 plus my X. Well, that's easy to solve for, right? Because you just got to move this X to itself, or get this 26.7 to the other side. So I can take 26.7 grams away from both sides. And of course, I get down to something like 10.0 grams equals X. And that's it. So in this reaction, apparently we get 10 grams of water if it is done correctly. Now you might say, Mr. why'd you write the 0 here? Remember, this is subtraction. 3 sig figs here, 3 sig figs here. Doesn't matter really in this case. What matters is the number after the decimal. And even though I get 10 here, I need to add in that last 0 for the right number of sig figs because I had decimals in each case. So I know that 0.0 exists. Is that going to really matter on a test? Less so, right? What I really care about on a test is you knowing this. Is it going to matter on a homework? Sure. Because I want you to make sure you're still practicing with sig figs, so when we're in a lab, we're getting better at using these things. In general, these slides and these questions, they're not that terrible, right? It's just really simple algebra. You don't let the questions, because they're full of chemistry, scare you. This should be pretty straightforward stuff. All you're doing is kind of solving for x and making sure both sides of the equation stay equal. As long as you think of it like this, these problems will be easy and you can breeze right on through them. I've given you a little bit of homework over that tonight, so you can try that out. And hopefully you'll find it pretty straightforward. If you get stuck, feel free to email me, but first try asking a couple other people in the room who seem to get it. Because that'll save me a little bit of time while I'm on Kairos. In the same breath, you'll get your answer right now instead of later tonight or tomorrow whenever I can answer it. So, okay, just a couple reminders before I let you get to work. Your sub here in a moment is going to pass out a worksheet to you over extensive and intensive and chemical properties and the kinds of problems we just did together on conservation of mass. That's going to be collected by your sub tomorrow. So that's homework. It's on my homework already, but get that done. And bring it in tomorrow. If it's not in with your sub there, I'll count it late. As long as your sub here recording is being present today. So that is homework tonight. And a reminder that you have a quiz over the first 30 elements and symbols on the periodic table on Friday. Again, we talked about that yesterday in class. You know it's coming. It's 12 points. It's an easy 12 points and 15 questions. But you've got to be working on memorizing this. Remember, there's a Quizlet or any other way you'd like to study for it. Just make sure you're practicing that alongside as well so we can get ready on it. So I'll see you back here again tomorrow, and we'll talk a little bit more about properties, and we'll move forward with this unit. Until then, good luck, and have a good one.